So conservative forces and potential energy, they all center on this idea of work that we've been using. And remember, work is the integral from some initial position to some final position, I'm just going to call it x here, of a force dotted with that displacement. So in other words, you've got, say, a final position here and your initial position there, and maybe you walk like that. So that's your displacement. That's the path you're walking on. We'll call that path A. Or you might choose to get from your initial position to your final position by wandering around like this. So kind of back and forth and all the way around. So walking, we'll call that path B. Either of those will get you from the starting point to the ending point here. But obviously they're very different paths, so the integral will be different. And so for example, if you were to look, if the force that we were looking at was drag, then the amount of work that you did on these two paths would be super different. The work done on path A would be a lot smaller than the work, if we're looking at absolute values, better specify that, than the work done by path B. You'd lose a lot more energy on path B than you would be doing on path A for drag, because remember, drag is always opposite the direction of the motion, so the force is always going to be opposite the way we're moving here. And if we go just real quickly on a short path, we'll lose some energy, but if we take this long winding path, we'll lose lots and lots of energy. So the amount of work depends on the path you choose. In this case, A or B or, some other path. And that is true in general, true for drag, true for friction, and really for most forces. However, for some special forces, that's not true. So one example is gravity. For gravity, the work done on path A is equal to the work done on path B. And this is, a little difficult to prove. You need some vector calculus concepts to do with that. But as long as you're okay with this idea that you can have some forces where the work, whether you choose to go this way or you choose to go on this long winding route, and the work is going to be the same, that's the concept we really need here. And this, if you're using mathematical terms, means the work is path independent. That is, it doesn't matter if you pick path A or path B, the amount of work is going to be the same. It actually just depends on those initial and final points. So just where you start and stop, that determines how much work you do, not how you get from your initial to your final position. And forces that have work that are path independent, those forces, so this force, gravity in particular, is what is known as conservative. Most forces, drag forces and friction, all of those are non-conservative forces. Because in general, it does depend on how you get from A to B. But for some special forces, they're path independent and they are conservative forces. And there's an interesting consequence of this. So if it doesn't matter which path you choose on, we could go ahead and just say, all right, so for example, if you go on path B, say you gain 4 joules of energy. That is to say, the work done by gravity on this path is equal to positive 4 joules. Whatever object is going from here to there, it's gaining 4 joules of energy because gravity, is pushing it down, and it's moving down, and it's picking up speed, and so it's picking up kinetic energy because of gravity. If gravity is path independent, that also means path B, the work done by gravity is also positive 4 joules. But if we know this, what if we turned around? What if we went from x final to x initial? So instead of traveling downwards, we traveled upwards, like this, which I will write in pink. So if we go from x final to x initial, that is, we walk backwards, then we lose that energy. So the work done is negative 4 joules. So here we're traveling back the other way. And remember, with the dot product, it's looking for the parallel, anti-parallel component. So if we go up, gravity's pushing down, it's taking the energy out. So if you gained 4 joules of energy this way, you lose 4 joules of energy that way. And why I point this out is because this brings up another property of path-independent works and conservative forces that's really important. Namely, that if you start at one place and you travel around in a circle, you are going to have the total work done on you by that force is going to be 0. And looking at our example here, so if we travel from the initial, we are gaining 4 joules of energy as we walk on this way, but then we travel back this way, we lose that energy again. So a corollary here is if you end up at your starting point, that is, you travel in a circle, the total work done by these forces, the conservative forces, is 0. So anywhere the force has taken energy away from you on the path, somewhere else on the path, it's going to give that energy back to you. So it sort of holds on to the energy for you. And because of that, we can then do something super useful for solving problems. Because these conservative forces hold on to the energy for you, they take it away on one part of the path, like this part, but then they give it back to you if you retrace your steps and end up the same final position. These conservative forces can be modeled as having what are called potential energies. So even though forces are an interaction, so in gravity, this little object as it ravels around is interacting with the Earth and it's exchanging energy with the Earth, we can model that conservative force, that work done by that force, as the Earth kind of like hanging on to the energy for the object and then giving it back later. So the math for that is we use U for the potential energy. So the change in your potential energy due to this force, so remember that delta, this guy right here, the triangle, that means change in U. That is the minus the work done by the conservative force. So remember, that's for conservative force, the work done by a conservative force. It's negative that, which means it's negative this conservative force dotted with the displacement. And because the potential energy, the change in potential energy goes like minus the integral of the force, we can get the force back by doing negative the derivative of the potential energy. And, putting the vector in as well, because the force is a vector. And in fact, if you want to do this in 3D, then you can use a cool concept called the gradient. So then the force this conservative force is negative the gradient, which we symbolize that way, and it looks all intimidating, but what it really means is we do negative the derivative with respect to x, and that's the x piece of the force, and negative the derivative of the potential energy with respect to y, that's the y piece, and negative the potential energy with respect to z, that's the z component of the force, and you don't have to remember any of that, but it's just kind of cool. All you have to remember is if you've got a potential energy and you take its derivative, that'll give you back the conservative force that's associated with it. And why we care about this? Well, let's pull out another sheet of paper and say, all right, so let's look at some examples, because they will show us why we care about this. If we've got gravity, well, the work done by gravity is equal to minus the force of gravity, mass times g, that 9.8. And then in the problems that we did earlier, we discovered that it's the final height minus the initial height. So h's are heights here. It actually doesn't matter what your horizontal position is, you know, kind of if you're off to the left or the right. It just matters how far away from the earth you are, what your height is. So if that's the work done by gravity, then the change in an object's potential energy, if we're thinking of the work done by gravity's potential energy, well, that's negative the work done by gravity, so that's just force of gravity, m times g, and this change in height. Final height minus the initial height. And if you have the spring force, that's one of the other conservative forces. Well, the work done by the spring is negative 1/2 the spring constant, and then your final distance from the equilibrium minus your initial distance from the equilibrium, both of those squares. So remember, x here is the change from the equilibrium length of the spring. So we've really got a delta x going on in here, but that's the work done by the spring, and the change in the potential energy that's held onto by the spring is the negative of that. So we just get rid of that negative. It's 1/2 k x final squared minus x initial squared. And why that is so useful? Well, one, now that we've got the work, we just have to plug in all of these things, and you notice it only matters on your initial and your final position, kind of the position that is telling you about the change from equilibrium of the spring, if you're talking about the spring force, or the height, the final and initial height, if you're looking at gravity. And going back to the most important equation for the work energy theorem, the work energy model, which is the work energy theorem, which is the equation we use in pretty much every single work and energy problem we do, which is that the work done on an object or a system is equal to the change in energy. Well, now we can split this work up into two kinds. We can do the work done by the non-conservative forces, so things like drag, friction, just random pushes and pulls, and the work done by conservative forces, so things like gravity and the spring force. And they're equal to, well, the only kind of energy we had was kinetic, so change in kinetic energy. And we are just going to take the work done by the conservative forces and move it over to the other side of the equation. Think of it like an energy rather than a work. So work done by those non-conservative forces equals the change in kinetic energy minus the work done by conservative forces. But we know the work done by conservative forces minus that is just the change in the potential energy associated with those forces. So the work done by those non-conservative forces, we'll write it all out because we're getting to the end, it's important to remember that, is equal to the change in the kinetic energy And then we sub in the change in the potential energy. So plus the change in the potential energy. And these two together, kinetic and potential, we're looking at the change, and we call this the mechanical energy. So the mechanical energy, that's the kinetic energy plus the potential. So the kinetic, that's like 1/2 mv squared, and the potential, well, maybe you have some from gravity, so that would be mg times your height plus a constant, because it's from the integral, remember, and then 1/2 the spring constant times that difference from equilibrium length squared plus a constant, because there's always a constant here. But these guys are the mechanical energy. And they're called the mechanical energy because if you notice, what they depend on are the motion, that speed, or the position. So height, if you're looking at gravity, sort of the end length of the spring, if you're looking at spring force. So they just depend on how an object is moving, really, you know, and the mass or the property of the spring, gravity. So these guys are relatively easy to calculate, and even more exciting if the work done by these non-conservative forces is zero. That is, these non-conservative forces like drag or friction or just random pushes or pulls, they're not sort of contributing any net energy into the system or taking any net energy out. So no outside energy in or out. We call that an isolated system. And we call it an isolated system because it's not passing energy back and forth with anything outside of it. So in this case, if you've got an isolated system, well, that's zero. This guy's zero, so that means the change in the kinetic and the potential energy is also zero. So we say then the mechanical energy is conserved. In other words, delta K plus delta U equals zero. And what that means is, you know, your kinetic energy that you have at time 1 plus all the potential energy you may have at time 1, they've got to be equal to the kinetic energy you've got at time 2 plus the potential energy you've got at time 2. So if you know this is true, if you know that nobody's stealing energy or putting energy into your system using those non-conservative forces, then if you can figure out what your total energy is at one point in time, you know it at any point in time. Sometimes it may be more kinetic energy. You've moved all the energy in the system off to kinetic, to where things are moving. At a different time, maybe more of its potential energy. You've taken some of that kinetic energy and you've put it over into these conservative forces and they're hanging on to it for you so you can use it later. But when you add up the total sum, it's got to be the same number every single time because the energy is not going in or out. Nobody is doing work from the outside of the system except for those conservative forces, but we are now modeling them as energies inside the system. So that is what is important about conservative forces and potential energies.